Okay, this is part 3 of our topic 8.12 in the AP Calculus curriculum, volume of washer method revolving around other axes besides the X and Y axis. In this video, we're going to do a couple of examples revolving around other vertical axes other than the Y axis. We're going to start by looking at the region R bound by the curve f of x equals 2 square roots of x and g of x equals 2/3 x plus 4/3. We're going to find a volume of the solid generated by revolving R about the line x equals -1. And as always, we will start by graphing this region. Curve 2 square roots of x is going to look like that. And the line g of x equals 2/3 x plus 4/3. It's going to look like that. Let's make this a little bigger so we can, let's make this where we can work with it a little better. Let's say that's the curve f of x. Oh, sorry, didn't know what that was. That's the curve f of x. And let's call this the curve g of x. And then the line x equals -1 is here. And so what we're going to be doing is looking for this region R rotated about the line x equals -1 with that inside washer taken out. So as we always do when we're dealing with rectangles perpendicular to the y-axis, we're going to solve these equations for x so that we can invert the axes. This is y equals 2 square roots of x. And I'm going to divide both sides by 2 and square both sides and get x equals y squared over 4, or 1/4 y squared. And then we're going to do the same with this curve. So y equals 2/3 x plus 4/3. Multiply both sides by 3 and get 3y equals 2x plus 4. Subtract 4 from both sides. And then divide by 2 and get 3/2 y minus 2 equals x. So now if we graph that with the y-axis horizontal, well, there we go. And the x-axis vertical, this was the x-axis, and this was the y-axis. And so when we graph 1/4 y squared, that's going to look like this. And we graph 3/2 y minus 2, that's going to look like this. And what we can see is where those two are going to be equivalent. Let's look at this. Let's go ahead and set these two equal to each other to get y. And so I got 1/4 y squared equals 3/2 y minus 2. If I multiply both sides by 4, I'll get y squared equals 12 over 2y, which is 6y, and then minus 8. So if I get everything on one side so I can solve, I get y squared minus 6y plus 8 equals 0. That means y minus 2 times y minus 4 equals 0. So y equals 2 and y equals 4. So those are the values of y we're looking for to integrate from. Y equals 2 to y equals 4. And this time where x equals -1 is the region we're integrating, or we're revolving around. So if I take one of the tall rectangles to generate the outside disk, remember, we revolve that around to generate the outside disk. That's going to give me the large disk. And then we'll cut the middle out in a minute. So the height this time is dy. And also, this is my linear equation. So the radius of that disk is 3/2 y minus 2. So the volume of one of those outside disks is going to be pi times the radius squared times dy. Then next, I'm going to draw the inside rectangle. And the height of that rectangle is going to come from my quadratic 1/4 y squared. And when I revolve that, it's going to give me the smaller disk that we're going to remove from the outside disk. Still dy is the height. This time the radius is 1/4 y squared. And so the volume of that inside disk is going to equal pi times the radius squared. 1/4 squared is 1/16, and y squared is y to the 4th times dy. And so that means that the volume of a region is going to be the volume of the outside disk minus the volume of the inside disk, which is going to be pi times the integral from y equals 2 to 4 of the large disk, 3/2 y minus 2 all squared times dy minus pi times the integral from, it's 2 to 4 of this time. It's going to be 1/16. I can go ahead and pull that 1/16 out. And this is going to be y to the 4th dy. We could integrate this by hand, but I really don't have room here, so I'm going to just type this in the calculator. This time because, well, it is. We'll do the first integral. So I'm going to do math 9, integral from 2 to 4. And I'm going to open these other parentheses inside like we always do. Instead of 3/2, I'm going to put 1.5 just because it's easier to type in the calculator. I'm going to replace in that TI-84, the y's with x's. Minus 2, close parentheses, and then square that because that's inside the integrand. And then the variable I'm integrating with respect to has to be consistent with what's inside the integrand. And then minus, now I haven't multiplied by pi, but I am going to go ahead and multiply this one by 1/16. Then I'm going to do the integral. Oops. Math 9 from 2 to 4. And this is going to be y to the 4th or x to the 4th in the calculator. Oops. Put it in the limit. And then integrate with respect to the variable inside the integrand again. And when I get my answer, I'm going to have to multiply by pi. I got 1.6, and now I'm going to multiply that by pi. And I'm going to end up with 5.026 or 5.027 units cubed. That's one we could integrate by hand. You might see something like that show up from time to time on the non-calculator part, but we could integrate this as a polynomial. You can do the u substitution, or you can go ahead and expand it and just integrate it term by term. Of course, this is a polynomial. So it is something we could do, or could see on the non-calculator part of either the multiple choice or the free response question to do an integral like that. If it was on the non-calculator part, you would have this answer left in terms of pi, of course. Let's do another example. We'll let the region R be bound by the graph y equals x, or by the y-axis, f of x equals cosine x and g of x equals sine x. And we're going to find the volume solid generated by the revolving R about the line x equals 5. As always, we start by graphing. And so we have y equals cosine x. We have y equals sine x. Oops, that's not really good. Sine x. Let's do this again. Cosine x, sine x. And we know that this intersection occurs at pi over 4. This is the x-axis, this is the y-axis. we know that this region is 1. We know that this y value is the square root of 2 over 2. And of course, this one is 0. And so this is my curve g of x. My red curve is f of x. And so we're going to solve these for yx like we always do. And we're going to get y equals cosine x, or x equals cosine inverse y. Arc cosine would be the same thing. Here we get y equals sine x. So x equals sine inverse y. We're going to regraph this oriented the way we're used to. And recall that we're only really looking for the values here, where now we got y-axis here, x-axis here. And this one, y is going to be at 1. And so we're looking at something like this. So this is going to be when y is 1. This is going to be when y is the square root of 2 over 2. And then this is going to be 0. So this is the region that we're looking at revolving around the line x equals 5. So x equals 5 is here, not to scale. Whoops, my bad. I have reverted back to the original axis. X equals 5 is up here somewhere. And this is the region. I'm going to draw the large rectangle first, that when we revolve will give us the outside disk. And I need to know the height of that. And the height of that is going to be 5 minus, and this is coming from the sine inverse. And so this is going to be 5 minus sine inverse y. So when I go to set this up, my large disk, outside disk, it's going to have dy, and the radius over here this time, is going to be 5 minus sine inverse y, or arc sine if you prefer. So the volume of my outside disk is going to be pi times 5 minus sine inverse y squared dy. Then I'm going to generate the inside disk, which is still dy. This time, the height of the inside disk, I should have erased that sine inverse there. 5 minus sine inverse no longer applies. So the height of this is going to be 5 minus cosine inverse y. And the volume of that inside disk is going to be pi times 5 minus cosine inverse y squared dy. So the volume that I'm looking for, that's one single washer, and we're integrating from y equals 0 to pi over 2 so that we get this region rotated about the line, x equals 5. So we're going to go from y equals 0 to y equals square root of 2 over 2. So this is going to be pi times the integral from 0 to the square root of 2 over 2. And the inside, or the outside, is going to be 5 minus. Hey, can you hold on just a second? I'm almost done with this video.
Yeah, you're good.
Okay, sine inverse y squared dy minus pi times the integral from 0 to square root of 2 over 2 times 5 minus cosine inverse y dy. And you can evaluate that on your calculator. Those are ones we wouldn't have to evaluate by hand. They might be ones on the FRQs where you set the integrals up and don't have to evaluate, or you might have them on the calculator portion where you would have to evaluate them on the calculator. But those are a couple examples of revolving around the other vertical axis besides the y-axis, or the x-axis. Sorry, the y-axis.